Are we ready? Can you confirm that that I pressed the right button, that I'm not Leo this time?
Yes, you are not alone.
Please, I need your attention, particularly those that have done 3 and 4. Then you can see the mistake you made either in the logic or presentation. Okay? I need your attention now. Okay, so when n is 1, actually n must be greater than or equal to 4. Because when n is 1, 1 is not greater than 2. When n is 2, 2 is not greater than 4. When n is 3, 6 is not greater than 8. But when n is 4, 24 is greater than 16. That's why the question says n must be greater than or equal to 4. So your Pn, if you want to test the preliminary ones, you only start from 4, 5, and so on. Okay? So, of course, our Pn is the statement n factorial greater than 2 to the power n for n greater than or equal to 4. That's our Pn. Okay? So you are going to try P4. P4 is 4 factorial, which is 24, which is greater than 16. Remember, 16 is 2 raised to the power 4. Okay? I just test that. You can do the way you write it might be different, so that's fine. So we're going to assume Pk is true. Assume Pk is true. What does that mean? It means k factorial is greater than 2 raised to the power k. Of course, k must be greater than or equal to 4 as well. The condition is also binding on your inductive hypothesis. Am I making sense? Now, so we prove Pk plus 1. What is that Pk plus 1 statement? It means k plus 1 factorial must be greater than 2 raised to the power k plus 1. Right? So that's what you want to show. So we start from the left side. Your k plus 1 factorial is k plus 1 times k factorial, right? So with your knowledge of factorial notation, you are able to achieve this. Now, we know that this is greater than 2k, 2 raised to the power k. So if this is greater than 2 raised to the power k, it means the product is greater than k plus 1, right? 2 raised to the power k. Okay? So the only thing is, this is what we want to achieve, right? We want to be able to show that this is 2 raised to the power k times 2. Greater than 2 raised to the power k times 2. Talk to me, please. So the only thing is, we need this to be greater than 2. Or to be equal to 2. But of course, this is greater than 2. Since your k is greater than or equal to 4, if you add 1 to whatever k is, it must be greater than 2. If even k itself is greater than 2. Does that make sense? So, remember, this means k plus 1 factorial. Clarissa, this is what I'm saying. Implies that I still have my greater than. This line implies that. The implication of the line. Okay? This step, the implication is that k plus 1 factorial is greater than 2 times 2 raised to the power k. Since k plus 1 is greater than 2. You can just put that additional comment to show that I really know what I'm doing. I'm not just walking towards the answer because it's convenient, but because this is logical. Does it make sense now? This is greater than this, since this is greater than 2. That's why the product is greater than 2 times that. We've talked about it before. If 3 is greater than 1, when you multiply both sides by something, it used to be greater. So 5 times 3 must be greater than 5 times 1. Okay? So that's what is happening here. This is the constant. If this is so, basically, k plus 1 is greater than 2, right? If you multiply both sides by 2 raised to the power k, that's what you have here. Does it make sense? And this is the first one, this is the second one. So you still have your greater than inequality. Any question? And this is what you want to achieve. So this implies that k plus 1 factorial is greater than 2 raised to power k plus 1 because this is 1. And this is your Pn plus 1 statement to be proved. And that's it. You just conclude. Okay? This implies that Pn plus 1, Pk plus 1, sorry, is also true. Therefore, Pn is true for all n greater than or equal to 4. And the second, the last one, there are other inequality problems which I want you to attempt in that worksheet. So the last but not the least, if you test n is 1, n is 0, because you start from 0, you get equality. And it makes sense because the instruction says it should be greater or equal to. So it doesn't matter if it is just equal. When n is 1, it is still true. When n is 2, that is when it is strictly greater because you get a 9 and you get 7. Yes? So it doesn't matter which one you do. So you can do n is 0, n is 1, n is 2, pick any one or two of them is fine. So I'm just going to start from the inductive hypothesis stage. So assume Pk is true. What does that mean? That means 3 to the power k is greater than or equal to 1 plus 2k. That's your inductive hypothesis. Karen, you're still looking at this. Are you lost? Do you understand this? Were you listening when I explained this? Are you sure? So now you should listen to this so you don't get lost again. So this is your inductive hypothesis. Yes? So for the case of Pk plus 1, to prove Pk plus 1, what does that mean? You want to prove that, so I write that in a different ink. This is what we want to achieve. Yes? So you can just simplify that to see what you intend to achieve. What we intend to achieve here is 1 plus 2k plus 2, which is 3 plus 2k, basically. Right? That's what we want to achieve. So if we are able to achieve this, then we are done. We just need to write it properly. Okay? So, we'll start from the left-hand side. 3k plus 1 is equal to, yes? Is equal to 3 raised to the power k times 3. And we know that 3 to the power k is greater than this. Then the products, 3 raised to the power k plus 1, will be greater than or equal to 1 plus 2k times 3 now. Yes? From our inductive hypothesis. Okay? So I can say since 3 to the power k is greater than or equal to 1 plus 2k. So we just brought that in. Okay? So this means that 3 to the power k plus 1 is greater than or equal to, I'm just repeating it, but in the simplified form. 3 plus 6k. Yes? But we only need 3 plus 2k. Of course, 3 plus 6k will be greater than 3 plus 2k. So this is greater than 3 plus 2k. Yes? So which means we can write this as 3 to the power k plus 1 is greater than or equal to 3 plus 2k. Since our 6k is expected to be greater than or equal to 2k. Even if your k is 0, then it will be equal. Right? But if your k is 1, then it will be greater. So that's why I said greater than or equal. So I should use greater than or equal here as well. Because it depends on what k is. K also has the property of n, and n could be from 0. Does that make sense? So with these two, now, this of course looks like what we want to achieve, right? But that's not the format of the question. So I'm going to try to write it in the format of the problem, which is this. First, by separating 1, 3 to the power k plus 1 will be greater than or equal to 1 plus 2k plus 2. Yes? I'm just trying to write it the way it should look. I only use this as a trick to know what I intend to do. Okay? Finally, 3 to the power k plus 1 will be greater than 1 plus 2k plus 1. Now it looks exactly the way I want it. Okay? This is now my pk plus 1. You can now conclude that this means that pk plus 1 is also true. Therefore, the statement is true for all n. Okay? But whatever logic you use, it must be, you must be able to defend it. It shouldn't just be on the basis of, oh, it's very convenient, that's why I use it. Yes, sir.
I then, this is, for both of them, I use a slightly different one.
Okay, let's see.